Welcome back. In the previous video, I explained you how you can linearize any nonlinear system or any nonlinear differential equation, right? In this lecture, I explain you how you can study the behavior of the fixed point from the eigenvalue of the Jacobian matrix, right? So, in the previous lecture, I say you if we can express any nonlinear differential equation in this Jacobian matrix form, which is u dot v dot equals to del f by del x, del f by del y, del g by del x, del g by del y into uv. So here u and v are two eigenvector, right? So if we can express any nonlinear differential equation in this Jacobian matrix form, then the system becomes linear near the equilibrium point where the linearization process goes on, right? So as the system becomes linear near the equilibrium point or the fixed point, so we can write the system in linear form, which is, let's say, x double dot plus bx dot plus ax, which is equals to 0, right? So this is a linear equation, linear differential equation. Why? Because the degree of the dependent variable x and its derivative is 1. That's why this is a linear differential equation. So we linearize a non-linear system, non-linear dynamical system in linear form, right? So we can write its solution as xt, which is equals to c1 e to the power lambda 1t plus c2 e to the power lambda 2t, right? So here lambda 1 and lambda 2 are eigenvalue of this Jacobian matrix, right? So what is lambda 1 and lambda 2? Lambda 1 and lambda 2 are two eigenvalue of this Jacobian matrix, right? So from the nature of this eigenvalue, we can say whether the fixed point is stable, unstable, or saddle, whatever it is, right? So let's consider the first case where both eigenvalues are greater than 0, means positive. So now let's erase this part. So this is our first case when lambda 1 and lambda 2 both are greater than 0. So what's our solution? Our solution is xt, which is equals to c1 e to the power lambda 1t plus c2 e to the power lambda 2t, right? So if we plot this solution along y, this is xt, and along x, this is t, time, right? So as lambda 1 and lambda 2 both are positive, then the solution is just like this, right? At t tends to infinity, x2 tends to infinity. So we can say that near the equilibrium point where the lambda 1 and lambda 2 both are greater than 0, this equilibrium point is unstable, right? So where lambda 1 and lambda 2 are greater than 0, this equilibrium point is unstable equilibrium point, right? So all system trajectories near the equilibrium point, just like this. Let's say this is a fixed point, right? And all system trajectories are diverge from the equilibrium point or the fixed point. or this is face portrait, face portrait, right? Or we can draw this face portrait as, let's say this is fixed point, this is unstable because all system trajectories are diverge from the equilibrium point. This is also unstable. This is also unstable, right? So from the given condition we can draw whatever the face portrait is becomes, right? So now consider second case where both eigenvalue are less than 0. Both eigenvalue are negative, right? So both eigenvalue is less than 0. So lambda 1, which is equals to let's say minus a, and lambda 2, which is equals to let's say minus b. So we can write that xt, which is equals to solution of the linear differential equation, because we linearize the nonlinear system, right? So the solution of the linear differential equation, which is c1 e to the power minus at plus c2 e to the power minus bt, right? So we can draw its along y, this is xt, and along x, this is time t. So as t tends to infinity, the solution tends to 0. So as xt, so as t tends to infinity, right, xt tends to 0. So we can say that the system, the fixed point where lambda 1 and lambda 2 both are negative, this fixed point is a stable fixed point. This is a stable fixed point. Fixed point. Now draw its face portrait. So face portrait, this is a fixed point. All system trajectories are converge towards the fixed point, right? Right? This is, let's say, fixed point. Or we can draw just like this. All system trajectories converge towards the fixed point. This is a fixed point, right? So now this is a stable, this is also stable, this is also stable. So this is case 2. Now let's erase this part. This is case 3. When one eigenvalue is positive and another eigenvalue is negative, what happened? Let's say lambda 1 equals to minus a and lambda 2 equals to b. So we can write its solution as c1 e to the power minus at plus c2 e to the power bt, right? So this is a fixed point. This is fixed point. So for positive eigenvalue, right? So this positive eigenvalue represent eigenvector like this, right? This is direction of eigenvector due to positive eigenvalue, right? So due to positive eigenvalue, system trajectories are diverge from the fixed point, and for negative eigenvalue, let's say this is the eigenvector or negative eigenvalue, negative lambda, right? And due to these eigenvectors, all system trajectories are converge towards the fixed point. So we can draw the phase portrait near this fixed point just like this, right? Just like this. And these kind of phase portrait where one eigenvalue is positive and another eigenvalue is negative, those phase portrait is known as saddle, 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 right? So now now let's erase this part, and our next part is case 4 when lambda 1 is alpha plus I beta in complex form, right? So and lambda 2 which is alpha minus I beta, right? What happened when eigenvalues are in complex form, right? So now xt is the solution as usual. Now c1 e to the power lambda 1 t, right? Let's break it. Let's see what happened. This is c1 and this is e to the power alpha plus I beta into t, right? So c1 e to the power alpha t into e to the power I beta t, right? So if we simplify this, it gives cos beta t plus I sine beta t, right? So this is xt, this is xt, this is alpha. This alpha is a deciding factor. This alpha decides whether the system is stable or unstable, right? So if alpha is negative, then the system is stable, right? If alpha is positive, then the system is then the system is unstable, right? And this part is a oscillatory part, oscillatory part. This is oscillatory part. So now consider when alpha is negative, what happened? If alpha is negative, let's draw xt. So along y this is xt and along x this is time t. So if alpha is negative, when here alpha is negative, right? So this is xt versus t graph, and the phase portrait, this is fixed point, this is fixed point. All system trajectories are moving towards the fixed point. This is the fixed point, right? Right. So this is when alpha is equals to negative, then it is stable phase portrait. Stable phase portrait. Why? Because at t tends to infinity, xt tends to 0, right? And what happened when alpha is positive? So if alpha is positive, then the fixed point is becomes unstable, right? Then the fixed point is becomes unstable. So along y this is xt and along x this is t. So right? So at t tends to infinity, xt tends to infinity, so we can say that the fixed point where alpha is positive, the fixed point is unstable fixed point, unstable fixed point, right? Now draw the phase portrait of this fixed point. This is fixed point and all system trajectories are moving outwards from the equilibrium point, right? And due to some oscillatory part, the system trajectories are moved outwards with some oscillatory motion, right? So I think this is the all cases. Oh, another case, when this alpha is positive and alpha is negative, what happened if alpha is 0? So if alpha is equals to 0, so then the system is the only oscillatory part, right? And the system of the fixed point is known as center, right? So this is the and the phase portrait is just like this. This is the fixed point and this is the phase portrait, and this direction is depend on the given situation, right? So this is all cases of eigenvalue, right? This is all cases of eigenvalue. And now erase this part and take an example of it and draw a phase portrait. Now take an example which is draw the phase portrait for the system which is equals to x double dot equals to minus sin x. This is very known system of oscillatory motion of pendulum. So draw its phase portrait. Our goal is to draw these equations phase portrait. This is a system of oscillatory motion of pendulum. So now let xt, which is equals to y, and y dot equals to minus sin x, right? So this is 1 and this is 2. This is 2 coupled differential equation, right? So why this is coupled? In the previous video I say that if equation of x is dependent on y and the equation of y is dependent on x, that's why equation 1 and 2 is known as coupled differential equation, right? Now, right, it's Jacobian matrix which is A, which is equals to this is f and this is g, right? So here this is del f by del x which is equals to 0, here del f by del y which is equals to 1, here del g by del x which is equals to minus cos x, here del g by del y which is equals to 0. So this is just Jacobian matrix, right? So this is Jacobian matrix. This is Jacobian matrix. So find its fixed points. So its fixed point are, and n is equals to plus minus 1, plus minus 2, 0 up to यूं ही चलते रहेंगे. So let's find the eigenvalue for 0, 0 fixed point. So we draw the phase portrait for 0, 0, pi, 0 and minus pi, 0. Right? We can draw only these 3 fixed points. So for 0, 0 fixed point, for 0, 0 fixed point, eigenvalue determinant of a minus lambda I, which is equals to 0. So minus lambda 1, this is 0, cos 0, which is minus 1, this is minus lambda, which is equals to 0. So lambda square plus 1, which is equals to 0. So lambda square, which is equals to minus 1, which implies that lambda equals to plus minus I, right? So can say that from the previous concept which I discussed, that the 0, 0 fixed point, this is 0, 0, this is pi, 0, and this is minus pi, 0. Due to this 0, 0 fixed point, the phase portrait is just like this, centered. This is centered, right? So this is due to 0, 0 fixed point. Now erase this part. Now consider pi, 0. Find the eigenvalue for pi, 0. So again, determinant of a minus lambda I, which is equals to 0. Now minus lambda 1. So cos pi, which is equals to minus 1, and minus 1 plus 1, and minus lambda, which is equals to 0. Now lambda square minus 1 equals to 0. So lambda equals to plus minus 1, right? So we can say that this is saddle. This is saddle. And let's find the eigenvector for plus 1 eigenvalue. So how we can find the eigenvector? So put the value of lambda here. This is minus 1, 1, 1, minus 1 into x, y, which is equals to 0, 0. So this is minus x plus y, which is equals to 0. So we can say that x equals to y, right? This is positive eigenvalue, and due to negative eigenvalue, the eigenvector. Now erase this part. Due to minus 1 eigenvalue, find the eigenvector. So this is minus 1, minus 1, minus 1, plus 1, this is plus 1, this is plus 1, and this is also plus 1 into x, y, which is equals to 0, 0. So this is x plus y equals to 0, and you can say that x equals to minus y. So this is 0, 0, this is minus pi, 0, this is 0, 0, and this is pi, 0. Right? Due to positive eigenvalue, the eigenvector, something here, this is the direction of eigenvector due to positive eigenvalue, and due to negative eigenvalue, this is, let's say 1, minus 1 is a eigenvector, and this is 1, 1. So this is 1, minus 1, right? So due to positive eigenvalue, all system trajectories are diverge. Due to negative eigenvalue, all system trajectories are converge. So this is the phase portrait. This is the phase portrait near pi, 0 fixed point, right? Similarly, minus pi, 0 fixed point, this whole thing is same as usual. Everything is same, and here we consider that we rotate these things just like this, minus x equals to y, and the eigenvector for negative eigenvalue, which is minus 1, 1, and due to positive eigenvalue in minus pi, 0 fixed point, the eigenvector is minus 1, minus 1. So this is minus 1, minus 1, right? And the system trajectories are diverge. The system trajectories are diverge, and due to negative eigenvalue, which is minus 1, 1, this is converge, as this is negative eigenvalue. So here the system trajectories are just like this. Right? This is minus pi, 0 fixed point. Now erase whole things, and let's draw the phase portrait of x double dot minus sin x in globalized form. Right? Let's erase this. So this is pi, 0 fixed point. This is 0, 0 fixed point. This is minus pi, 0 fixed point. Right? Due to positive eigenvalue, the system trajectories are diverge. due to negative eigenvalue the system trajectories are converge, and here also this is a negative eigenvalue, the system trajectories are diverge, and due to negative eigenvalue the system trajectories are converge towards the fixed point. This is fixed point, this is, and this is fixed point, right? So in 0, 0 fixed point the system trajectories are centered, right? This is centered, and here this is saddle. So in this given situation we can draw just like this. So this is the face portrait of, this is globalized face portrait. This is global face portrait of this x double dot minus sin x, right? So that's all for this video, right? So if you find this video helpful, don't forget to like, comment and subscribe.